Imagine staring through a microscope at an embryo. For 3 full days, you've watched it divide flawlessly, going from a single fertilized oocyte to 2 cells, then four, and then an 8-cell picture of just breathtaking symmetry.
Right. It's glowing with potential at that point.
Exactly. It has all this potential. And then on day 4, it just stops.
Yeah.
There's no contamination in the dish, no power outage, no obvious warning signs at all. It just crashes.
Which is, it's the ultimate puzzle.
It really is. And, to the patient waiting for that phone call, it is an absolute tragedy. But to a modern embryologist standing in that clean room, it's basically a forensic crime scene.
That's a really good way to put it. It completely captures the tone we're setting today.
Well, welcome back to our deep dive into inside the IVF lab. If you joined us for our last deep dive, we talked all about oocyte freezing and fertility preservation. But today, for episode 24, we are getting into troubleshooting in the IVF lab.
Yeah. And when a cycle yields an unexpected or poor outcome, the laboratory entirely transforms. I mean, the clinical production side just pauses, and the room becomes a forensic suite.
Which is so fascinating. You guys basically become detectives.
We do. We act as detectives, performing a really intense, multi-point scientific interrogation of the environment, the chemistry, and the cellular biology itself.
And that is exactly what we are mapping out for you today. Because by the time we finish this conversation, you're going to have a complete mental map of how embryologists separate the unpredictable, chaotic nature of human biology from systemic environmental breakdowns.
Right. We want to show how a modern lab offers absolute data-driven transparency rather than just guesswork or, blame.
Okay, let's unpack this shift in laboratory culture for a second, because it reminds me of how we handle aviation black box investigations.
Oh, that's a great analogy.
Right. Because when a commercial flight experiences sudden, severe turbulence, or say an engine pressure drops mid-flight, the investigators from the NTSB don't just run around the tarmac throwing accusations. They don't guess.
No, they methodically look at the data.
Exactly. They download the fuel logs, they pull the micro-weather data for that specific atmospheric grid, they look at the engine telemetry and systematically reconstruct the physics of the event.
Well, what's fascinating here is that the IVF lab operates on that exact same principle of systems engineering.
Really? Like exactly the same?
Pretty much, yeah. We maintain a blameless quality culture because that is literally the only way you guarantee that anomalies are actively reported.
Oh, I see. Because if people are scared, they'll hide it.
Exactly. Think about it. If an embryologist is terrified of being punished for a subtle deviation in a cycle, they might hesitate to flag it. They might just, hope nobody notices.
Wow. Yeah, that makes total sense.
Right. But when you establish a blameless, data-centric culture, a sudden drop in a patient's fertilization rate isn't a hidden failure. It's treated as an incredibly data-rich event.
So it provides the forensic clues required to optimize the medical strategy moving forward.
Yes, and it's vital to remember that biology is inherently variable. Even under perfect conditions, not every oocyte fertilizes. And not every embryo actually possesses the intrinsic capability to reach the blastocyst stage.
Which fundamentally changes the emotional weight of a setback for you, the listener, because getting bad news can feel like falling into a terrifying black hole.
It feels arbitrary.
Right. But when you realize there is a rigorous, unyielding scientific framework waiting to catch that anomaly, dissect it, and map it, it shifts the narrative entirely. The laboratory doesn't just shrug, they go to work.
We absolutely go to work.
So if we are going to act as forensic detectives today, let's start our timeline at the first major biological checkpoint, the morning after insemination.
Oh, yes, the day 1 postmortem.
Right. This is where we encounter total fertilization failure, or TFF.
Exactly. And just to set a baseline here, TFF occurs in roughly 1 to 3% of ICSI cycles.
Okay, so it's rare, but it definitely happens. Walk us through what you actually see.
Well, when we pull the culture dishes out of the incubators, usually 16 to 18 hours after the sperm injection, we are looking for the appearance of 2 pronuclei.
And those are from the sperm and the egg?
Right. One from the sperm, one from the oocyte, which indicates normal fertilization. But in a TFF event, you look through the high-power optics and you just see nothing.
Yeah, literally nothing.
Nothing. Not a single oocyte in the cohort has fertilized.
Which is just a devastating update to give a patient. But the investigation starts the second you see those empty cells, right?
Immediately.
So what is the very first thing you look for under that 400x magnification?
The first thing we do is assess the structural integrity of the oocytes themselves. We look closely at the plasma membrane. We're asking, are they lysed?
Lysed, meaning broken or ruptured.
Exactly.
Lyse?
Lysis means the cellular membrane has ruptured or degenerated.
Okay, and if they aren't broken, if they look intact.
If they are perfectly intact, we look for abnormal division markers, things like chaotic cytoplasm. But really, the most critical diagnostic step here is extrapolating backward in time.
Extrapolating backward, like checking the security footage.
Sort of, yeah. We need to review the exact developmental maturity of those oocytes at the very moment the sperm was injected the day before.
Because maturity in this context isn't just a subjective assessment of like how the cell looks to the naked eye. It's a highly specific mechanical phase of meiosis.
Precisely. We have to definitively verify if the oocytes had progressed from the M1 stage, which is metaphase 1, to the fully mature M2 stage, which is metaphase 2.
Okay, and how does an embryologist visually confirm that a cell is at the M2 stage?
By looking for the extrusion of the first polar body, it's this tiny packet of discarded genetic material sitting just outside the cell membrane.
I want to dig into the physics of that M1 stage for a second, because let's say a patient had a high number of M1s and an embryologist injected them anyway. What is physically happening inside that immature cell that prevents fertilization?
Well, if we connect this to the microarchitecture of the cell, an M1 oocyte is quite literally mechanically locked.
Mechanically locked. How so?
At the M1 stage, the cell's meiotic spindle, which is this delicate network of microscopic protein fibers, is still actively holding pairs of homologous chromosomes together.
So it's still sorting itself out.
Exactly. The cell hasn't finished separating its own DNA yet. It hasn't pushed half of its chromosomes out into that polar body.
And if you inject a sperm's DNA into that environment?
The oocyte's machinery is entirely misaligned. Just cannot process the incoming paternal genetics because it is still untangling its own maternal genetics.
Yeah.
It is a guaranteed mechanical failure.
I have to stop you there, though, because if I'm a patient reading a clinical report that says 0 out of 10 eggs fertilized, I mean, my immediate, highly skeptical thought is human error.
Oh, absolutely. That's a very common reaction.
Right. My thought is that the embryologist just missed the target. Or they crushed the cells with the needle, or maybe they let the dish get too cold on the bench.
Yeah, people assume it was a handling issue.
So how can a lab definitively prove to me that they didn't just have, like, a clumsy day at the bench?
That skepticism is entirely natural. And honestly, it is the exact reason our forensic audit protocols are so intense. We don't just assure the patient we didn't make a mistake. We mathematically chart technical variables against biological variables.
And if human error is suspected?
We go straight to the micromanipulator logs and the electronic witnessing system.
Okay, what are you looking for in those logs specifically?
We review the timeline and the execution. We confirm that the sperm immobilization protocol was completely standard.
Right, because before a sperm is injected, the embryologist uses a microscopic glass needle to gently strike the sperm's tail.
Yes, and that physical strike isn't just to stop it from swimming. It intentionally breaches the sperm's membrane.
Wait, really? You're breaking the membrane on purpose?
We are. It initiates a physiological reaction that allows its DNA to unfurl once it's inside the oocyte. So we check if that was done correctly.
Okay, so you check the strike. What else?
We review the needle penetration mechanics. Did the plasma membrane break smoothly during injection, or was there, like, unusual elasticity?
And if all those logs come back clean?
If the technical logs are flawless, the timing was perfect, and the oocytes were visibly at the M2 stage, well, we can confidently isolate the failure away from the human hands. We point it toward a profound biological mystery.
Which is an incredible pivot point. The mechanics were flawless. The oocyte had its polar body sitting at the M2 stage ready and waiting.
Yeah.
The sperm was immobilized perfectly and placed directly into the cytoplasm. And yet, absolute silence. No communication between the two.
Right. And this brings us to the oocyte activation paradox.
Which requires us to dive deep into the biochemistry of early life. Because normal fertilization is not just a physical merging of two cells, is it?
Not at all. It is a massive, highly orchestrated biochemical cascade. When a sperm enters the oocyte, it is required to release a very specific potent enzyme.
This is phospholipase zeta, right? Or PLC zeta.
Yes, PLC's up.
So the classic high school biology analogy here is the lock and key. The oocyte is locked, the sperm has the PLC zeta key, it turns the lock, and the cell opens.
That's the textbook version, yeah.
But I actually think that metaphor falls flat. It makes it sound like a static mechanical event.
Oh,
it's
yeah.
more like a biological match being dropped into a pool of gasoline, isn't it?
That is a much more accurate way to visualize it, honestly. When that PLC zeta match is dropped into the cytoplasm, it acts on the oocyte's internal structures.
Specifically the endoplasmic reticulum.
Exactly. The endoplasmic reticulum serves as a massive storage tank for calcium ions. The enzyme triggers it to release its reserves,
Yeah.
creating rhythmic, rolling oscillations of calcium.
So literally waves of calcium washing through the cell.
Literal waves. They pulse every few minutes for several hours.
That's incredible.
It is. And that rhythmic electrical shock is the definitive biological signal that tells the oocyte, hey, you are fertilized, resume your meiosis, and start dividing.
But what if the sperm is genetically deficient? What if it doesn't carry enough PLC-zeta?
Or if the oocyte's calcium tanks are somehow defective, right? They might be numb to the enzyme. In those cases, the match is struck, but the gasoline doesn't ignite.
You get no calcium waves.
Exactly. And the cell remains in suspended animation. Total fertilization failure.
So what does this all mean for the forensic detective? Once you map this out and suspect a PLC-zeta deficiency, you don't just write it in file and wish them luck next time.
No, not at all. We actively engineer a workaround.
What?
What's fascinating here is that we can employ artificial oocyte activation, or AOA.
Artificial activation, how does that work in the next cycle?
In the patient's subsequent cycle, we can intentionally bypass the sperm's broken enzyme machinery. Immediately following the ICSI procedure, we introduce a specialized chemical trigger to the culture dish.
A calcium ionophore, like ionomycin or A23187.
That's exactly.
Wait, I want to understand the exact mechanism here. When you say you introduce this chemical, how does a chemical sitting in a dish physically force calcium into the inner sanctum of the oocyte?
Oh, it's a brilliant piece of cellular manipulation. An ionophore is a lipid-soluble molecule.
Okay, lipid-soluble.
Right. And the oocyte's outer membrane is made of a lipid bilayer, which usually acts as a highly secure border wall, keeping extracellular calcium out.
So it's locked down.
Completely locked down.
Oh, right.
But when we expose the cell to ionomycin, the ionophore physically embeds itself into that lipid wall. It acts like a temporary microscopic tunnel.
Oh, wow.
Yeah, it permeabilizes the membrane, allowing a highly controlled influx of calcium ions from the surrounding media to flood directly into the cytoplasm.
So you are basically opening the floodgates from the outside.
We are. We bypass the internal endoplasmic reticulum entirely. We force the calcium spike ourselves, jump-starting the activation cascade artificially.
That is wild. And then what happens?
Once the wave hits, we wash the ionophore away. The membrane seals back up, and the cell wakes up.
It is a stunning example of how identifying the exact microscopic failure point allows us to design a direct, targeted biochemical solution.
It really is. You diagnose a microscopic enzyme failure, and you fix it with an engineered flood of calcium.
Okay, but let's transition out of day one. Let's say we've solved the first hurdle. The sperm and egg have communicated, the activation waves are perfect, and the cell starts dividing.
The engine is started.
Right. But getting the engine started doesn't mean the car won't suddenly stall on the highway.
Very true.
So what happens when an embryo looks completely flawless on day 2 and day 3, and then abruptly hits a brick wall on day 4?
This takes us into the territory of embryonic genome activation. We commonly refer to this in the lab as the day 3 wall.
The day 3 wall. It sounds like a marathon runner hitting the limit of their endurance.
That is precisely what is happening at the cellular level. It's one of the most critical biological checkpoints in early human development.
Why do embryos arrest here?
Well, to understand that, we have to explore the maternal to zygotic transition, or MZT.
Okay, MZT.
Right. During the first 3 days of development, the embryo is actually coasting. It is not using its newly formed DNA to survive.
Wait, it's not using its own DNA?
No, it's being powered almost entirely by maternal messenger RNA transcripts and proteins. These were stockpiled inside the oocyte during its long growth phase in the ovary.
So for the first 72 hours, the embryo is essentially living off an inheritance.
Oh, biological inheritance, yes.
The mother's biology packed a cellular suitcase full of fuel and instructions, and the embryo is just burning through it. It hasn't turned on its own genetic engines yet.
It is entirely reliant on those maternal reserves, but, those reserves are finite.
You run out.
Exactly. By the time the embryo reaches the 8-cell stage around day 3, those maternal transcripts begin to rapidly degrade. A complex mechanism strips the protective tails off the maternal mRNA, destroying them.
And at this exact critical juncture, the embryo's newly combined genome, the unique integration of the maternal and paternal DNA, must wake up.
The inheritance is gone.
It's time to get a job.
Yes, the zygotic genome must take over transcription. It has to start manufacturing its own proteins to drive the complex cellular machinery required to form a blastocyst.
This is the great genetic handoff.
That's a perfect way to describe it.
But what if that handoff gets fumbled? I mean, what if the unique combination of the sperm and egg DNA just doesn't mesh properly, or if there is a lethal chromosomal error hidden in the code?
Then you hit the wall. If an embryo is an absolute picture-perfect 8-cell stage on day 3, but suddenly fragments, arrests, and begins to degenerate on day 4, well, it strongly points to a transcription failure.
The intrinsic genetics simply couldn't fire up the engines.
Exactly. The blueprint was flawed.
I see this point causing a massive amount of friction and confusion for patients, because the myth is pervasive, right?
Oh, extremely pervasive.
A patient hears that their beautiful embryos all died on day 5, and their immediate thought is, someone at the lab killed them. Someone contaminated the dish. Someone left the incubator door open overnight.
This is such an important myth to dissect because it causes so much unnecessary anguish.
Let's debunk it then.
The reality of how a modern IVF cleanroom is engineered makes an external catastrophic contamination event practically impossible.
Practically impossible. That's a strong statement.
It is, but it's true. We are talking about environments fortified with aggressive positive pressure.
Meaning air only flows out of the room, never in.
Exactly. And we utilize industrial-scale HEPA filtration that traps microscopic particulates alongside specialized VOC scrubbers.
VOC is volatile organic compound.
Yes. Perfumes, cleaning chemicals, off-gassing from paint or plastics in the building. The scrubbers strip these toxins from the air before they ever reach the lab.
Wow, so the air itself is intensely filtered.
Highly filtered. Furthermore, the embryos aren't just sitting in open cups. They are cultured in microscopic drops of media, completely submerged beneath a thick, sealed layer of sterile medical-grade mineral oil.
So they are hermetically insulated from the room's atmosphere.
Right, so when we see late-stage arrest hitting that day 3 wall, it is almost exclusively a result of intrinsic genetic friction. It is a profound biological limitation, not a technician bumping a table.
But, and this is a massive caveat, to confidently sit across from a devastated patient and tell them, your embryo is arrested due to intrinsic genetics, the lab cannot just assume they didn't make a mistake.
No, you absolutely can't.
You can't just say, trust us. You must possess absolute, unassailable proof that your environment was flawless.
You cannot ethically claim biological failure until you have empirically proven environmental perfection.
And that brings us to the multi-point environmental audit, when the lab effectively puts itself on trial.
It's exactly like putting the lab on trial.
So if I'm the lead detective trying to prove the lab didn't cause the arrest, my first thought is the consumables, the liquid the embryos were living in. How do you audit that?
We initiate a rigorous media lot audit. We trace the exact bottle of culture media used for that specific patient's embryos.
And you're checking lot numbers.
We check the lot numbers and cross-reference them with the manufacturer's quality control certificates. But we don't stop there. We audit our own chain of custody.
What does that entail?
We review the delivery logs. Was the package shipped correctly on dry ice? When it arrived, was it immediately transferred to our secure refrigerators and held at exactly 4.0 degrees Celsius?
You check if it was ever exposed to ambient light or room air.
Yes, beyond the strict minute-by-minute protocol windows.
It really is a forensic chain of custody. You are proving that the fluid itself was biologically pristine.
Right. And then you have to audit the atmosphere.
The gas saturation audit. Because the incubators are not just warm boxes, are they?
Not at all. They're supplying a highly calibrated mixture of gases, usually a specific ratio of carbon dioxide, oxygen, and nitrogen.
And how do you verify that didn't fluctuate?
We pull the telemetry logs from the incubator's hard drive to ensure that the gas concentrations didn't drift by even a fraction of a percent during the 5 days of culture.
Even a fraction of a percent. That's incredibly precise.
And we physically check the main gas supply lines, the manifolds, and the regulators for microscopic pressure drops. If a secondary valve was sticking and the CO2 supply stuttered for an hour on day 3, we need to know.
And finally, the thermal audit, because temperature is the absolute baseline for cellular metabolism.
Exactly. We verify that the incubator chambers and the heated workstation hoods held an unwavering 37.0 degrees Celsius.
And you aren't just looking for obvious catastrophic failures like an incubator shutting off.
Oh, no. We are hunting for micro-oscillations. A shift of even half a degree back and forth over a 24-hour period can severely disrupt the delicate enzymatic reactions happening inside the embryo.
Which raises a really important engineering question. How do you know the digital display on the front of the incubator isn't just lying to you?
That's a great question.
I mean, if the machine's internal thermometer is broken, it's going to log perfect data while freezing the embryos.
Which is why a high-standard lab never relies solely on the machine's own sensors.
Oh, okay. What do you use instead?
We utilize an independent multi-channel telemetry system. This is a completely separate secondary electronic ledger.
So it's totally divorced from the incubator's own brain?
Exactly. We thread our own highly calibrated third-party probes through access ports into the back of the incubators. These probes record temperature and gas data independently, beaming it to a separate server.
Creating a tamper-proof forensic log.
Yes. If the incubator's internal sensor loses calibration and reports 37.0 degrees, but our independent probe reads 36.6, the system instantly triggers an alarm, and we catch the discrepancy before it impacts the cells.
We always have a secondary objective witness to the environment. That is an obsessive level of control.
It has to be.
But let's zoom in on one specific, highly volatile environmental variable that I know keeps embryologists up at night. You mentioned the culture media earlier, but the chemistry of that media is incredibly fragile, isn't it?
You're talking about the physics of dynamic pH drifts. And yes, this is where the biochemistry gets incredibly delicate and where handling speed is everything.
I love the chemistry of this. Here's where it gets really interesting for you listening. Let's think about this culture media like a highly calibrated carbonated beverage.
Okay, I like this analogy.
If you pour a glass of sparkling water or soda and just leave it sitting on your kitchen counter, the dissolved carbon dioxide gas bubbles escape rapidly into the room air, and the drink goes completely flat.
That is the exact physiochemical mechanism at play. Modern embryo culture media relies heavily on a delicate sodium bicarbonate buffering system.
So the media contains dissolved bicarbonate.
Right. To maintain a physiological pH of roughly 7.2 to 7.3, which is the extremely narrow window where embryos can survive, that media requires a continuous heavy atmosphere, 5% to 6% CO2, pushing down on it inside the incubator.
And the CO2 gas dissolves into the liquid, forming carbonic acid, which balances the bicarbonate and locks the pH in place.
Exactly.
So if a technician pulls a dish out of the incubator to look at it under the microscope, and that dish doesn't have a secure mineral oil overlay protecting the liquid, the CO2 gas in the media immediately starts escaping into the room air.
The soda goes flat.
Instantly.
Instantly. And the biological fallout of that gas loss is severe. When the CO2 escapes, the chemical equilibrium breaks, and the media undergoes an alkaline shift.
Meaning the pH rises, becoming more basic, shifting from a safe 7.2 up to 7.4 or even higher.
Right.
But to a layperson, 7.2 versus 7.4 sounds like a rounding error. Why does the embryo care about such a tiny numerical shift?
To a microscopic single cell, that shift is an absolute physiological earthquake.
Thing earthquake.
Yes. An alkaline shift directly and immediately stresses the cellular mitochondria, the microscopic powerhouses generating energy for the embryo. When the mitochondria are stressed by high pH, they decouple.
They stop producing ATP energy efficiently.
Exactly, and without ATP, the embryo's machinery grinds to a halt. To form a blastocyst on day 5, the embryo has to undergo cavitation.
Cavitation, that's forming the fluid-filled cavity, right?
Right. It has to actively pump sodium ions into its center to draw in water. Those cellular pumps require massive amounts of ATP.
So if the pH drifted high on day 2 because of poor handling,
The mitochondria are damaged, the ATP reserves are depleted, and the embryo simply lacks the raw energy to run the pumps on day 5. It arrests.
wow.
That is why we guard the media pH with our lives. Handling times outside the incubator are tracked in seconds, not minutes.
This is so dense and so intricate. The level of vulnerability these cells have is staggering.
It really is.
But it brings me to a huge mathematical question. Let's say a patient's cycle crashes on day 5. You pull the media logs, the telemetry, the pH audits. Everything looks perfect.
Okay.
Couldn't the patient still argue, well, maybe your independent sensors missed a microoscillation right when my embryos were on the bench? How do you mathematically prove that the lab wasn't the issue for me specifically?
If we connect this to the broader operational logistics of a busy clinic, that is where cohort comparison comes in.
Cohort comparison.
Yes, it is how we isolate the biological variable via cross-patient cohort mapping.
Walk me through the math of that. How does looking at other people's embryos mathematically protect the individual?
In a high-volume IVF lab, you are never just culturing one single patient's embryos on any given day. You are managing a cohort.
So let's say patient A unfortunately experiences total embryo arrest on day 5.
Right. To conduct our forensic investigation, the laboratory director immediately pulls the outcome files for patients B, patient C and patient D, whose oocytes were retrieved on the exact same morning.
And crucially, because they were processed on the same day, their embryos are being grown using the exact same lot numbers of culture media, the exact same batches of mineral oil, and they are sitting right next to patient A in the exact same bank of incubators.
Exactly. They share an identical synchronized laboratory environment. The physics and the chemistry applied to them were the same.
So it's a perfect control group.
It is. Now, if the culture media was subtly toxic, or if the incubator temperature actually did fluctuate in a way that telemetry missed, it would not selectively target patient A.
It would be a systemic issue.
It would crash the entire system, and we would see terrible outcomes across the board.
But if you look at the data,
If we look at the cohort data and see that patients B, C, and D all achieved beautifully expanded high-grade blastocysts from those exact same media drops in that exact same incubator, well, we have our definitive answer.
you have effectively and empirically isolated the variable.
Yes, we have.
The environment was proven to be fundamentally capable of supporting life because it supported life flawlessly for B, C, and D.
Therefore, by the basic laws of deduction, the arrest in patient A must be tied to the intrinsic biology, the genetics, or the specific cellular integrity of patient A's gametes.
It isolates the variable completely away from the laboratory and squarely onto the biology.
And I want to acknowledge that while that is an incredibly difficult and heavy clinical answer to give a patient, it is a scientifically honest one.
Right. It removes the agonizing mystery.
It stops the patient from wondering if they just chose a bad lab, and it focuses the medical team on solving the actual biological problem.
So once all of this forensic data is gathered, the TFF checks, the M1 and M2 maturity logs, the multi-channel telemetry audits, the pH mapping, the cohort comparisons, where does it go?
We synthesize the entire investigation into the root cause matrix and what we call the KPA framework.
KPA framework. But wait, how does the lab ensure this data doesn't just disappear into a filing cabinet?
Well, every high-standard laboratory is required to document unexpected anomalies through a formal root cause analysis, or RCA report.
What does the anatomy of that RCA document actually look like?
Oh, it is exhaustive. We start by clearly defining the anomaly, for example, total fertilization failure in patient X. Then we log the serial numbers of every single piece of equipment used.
Every piece.
Every single piece. We document the lot numbers of all consumables. We verify the human operator competencies. We check the training logs to ensure the embryologist who performed the ICSI was fully validated.
Making sure they demonstrated proficiency in that exact procedure within the last 6 months.
Exactly. And we chart the chronological timeline of the gametes minute by minute from retrieval to arrest.
And when you are drilling down into the data, you use a specific analytical methodology, right? The 5 whys.
I love the 5 whys. It's a classic technique borrowed directly from engineering and manufacturing quality control.
You drill past the surface symptom by asking why 5 consecutive times to find the foundational systemic variable. Give me an example of how that plays out in the lab.
Okay, let's say we had an issue with blastocyst formation. Why did the embryo arrest? Because the media pH drifted too high.
Why did the pH drift too high?
Because the protective oil overlay was too thin, allowing CO2 to escape.
Why was the oil overlay too thin?
Because the automated dispensing pipette was delivering 2.5 milliliters instead of 3.0 milliliters.
Why was it delivering the wrong volume?
Because the pipette had lost its internal calibration.
Why did it lose calibration?
Because our preventative maintenance schedule only required calibration every 6 months, which wasn't frequent enough for that specific model.
Wow, so you keep going until you hit bedrock. You hit the absolute root cause.
That's the goal.
And once you hit that bedrock truth, the RCA doesn't just end with a shrug.
Never. The RCA report must culminate in a KPA, which stands for Corrective and Preventive Actions.
Corrective and preventive action.
Right. The KPA is where the rubber meets the road. It means we formally update our standard operating procedures based on what the 5 whys revealed.
So in that example, the CPA would mandate moving from biannual pipette calibrations to monthly or weekly gravimetric calibrations.
Exactly. The KPA is how the lab permanently evolves. It is how we lock down the safety shield for every single cycle that follows.
So what does this all mean for the human being at the center of this? We've moved from the lab bench through the complex chemistry of calcium waves, through the environmental audits, and into the KPA framework.
Let's bring it back to the patient.
How does this mountain of forensic data change their medical future?
This is the entire point of the exercise. This is where the detective work pays off. We are re-engineering the roadmap.
The data extracted from a difficult, heartbreaking cycle is never wasted.
Never. We translate that failure into a highly customized, hyper-specific clinical strategy for the next attempt. The failed cycle becomes the ultimate diagnostic map.
So if a patient decides to try again, the team isn't just hitting the reset button and hoping for better luck. You are changing the physics and the chemistry of the next cycle based on the RCA.
Exactly. Let's say our investigation revealed that an embryo hit the day 3 wall particularly hard, and the cohort data suggested an extreme sensitivity to metabolic stress during the maternal to zygotic transition.
What do you do then?
The collaborative team, the laboratory director, and the reproductive endocrinologist might decide to fundamentally alter the culture media strategy for the next cycle.
Moving away from a sequential media system.
Yes, sequential media requires moving the embryo to a new dish on day 3. So we might switch to a single-step continuous media system, completely eliminating the microscopic stress of transferring the embryo during its most vulnerable genetic handoff.
Or if the issue is maturity.
If the day 1 postmortem showed too many M1 oocytes at retrieval, the physician will use that data to completely adjust the ovarian stimulation protocol.
Perhaps extending the timing of the trigger shot by 12 hours to push for better M2 maturity in vivo.
Exactly. Or, if we suspect a microscopic pH sensitivity, we might rewrite the handling protocol for that specific patient, cutting the allowable time the dish can be outside the incubator from 2 minutes down to 60 seconds.
We rebuild the entire scientific approach around the specific biological vulnerabilities we uncovered.
It's the ultimate silver lining. You have completely customized the science to the individual.
We have, because science doesn't claim to make every cycle work. That is an impossible promise to make when dealing with the staggering complexity of human reproduction.
It really is impossible.
But what modern embryology does promise, and what we deliver through this forensic anchor, is to measure every single variable with absolute, uncompromising honesty.
And when a lab can present clear, audited, empirical data, it removes the agonizing weight of the unknown from the patient's shoulders. They don't have to wonder what if. They know.
And I think that brings us to a really profound, final, provocative thought for you to carry with you as we wrap up. We've spent the last hour marveling at our mastery over the environment.
I really have.
We can perfectly audit the media lots down to the microliter. We can intentionally trigger the exact biochemistry of a calcium wave to bypass an enzyme deficiency. We can track thermal telemetry to the decimal point and map cohort outcomes to mathematically isolate a variable.
We control the controllable to the absolute limits of technology.
But eventually, all of this perfect science, all the sensors, all the HEPA filters, all the ionophores, it eventually forces us to confront the ultimate boundary of our control.
The profound, unyielding limits of human biology itself.
Exactly. At what point does science, with all its telemetry and diagnostic tools, simply have to step back, look at the genetics of a single cell, and humbly accept what it cannot change?
It's a humbling thought, isn't it? Standing at the absolute edge of what technology can engineer and looking out into the vast, uncontrollable mystery of human DNA.
It is the defining tension of our entire profession. We push the boundaries of the environment to absolute perfection, precisely so we can clearly see the biological truth, whatever it may be.
We strip away the noise the biology can speak.
And what an incredible journey it has been to explore that forensic framework with you today. Thank you for joining us on this deep dive into the command center of the laboratory.
It's been great.
But our journey isn't over yet. We are at the threshold of something even bigger. I want to officially tease our upcoming final Season 1 Deep Dive, Episode 25, Ethics, Uncertainty, and Decision-Making in Embryology.
That one is going to be intense.
It really is. In that conversation, we are going to leave the spreadsheets, the pH sensors, and the telemetry alarms behind. We are going to explore the deep moral horizons of reproductive science.
We will navigate the incredibly complex gray zones of PGT mosaicism, the deeply challenging realities of surplus embryos, and the profound emotional weight that embryologists carry as the silent, unseen guardians of early human development.
You absolutely won't want to miss it. Until then, keep asking questions and keep diving deep.